Machine learning is a fascinating field that explores how computers can be programmed to learn from experience and improve over time. Imagine a world where computers analyze medical records to suggest the best treatments for new diseases, or where your home learns your habits to optimize energy use. Even your personal assistant could adapt to your interests, highlighting news stories that matter most to you. The potential of machine learning is vast, opening doors to new applications and unprecedented levels of customization. In this video, we'll break down the basics, explore real-world examples, and see why machine learning is so important in today's data-driven world. Why is machine learning such a big deal? Some tasks are simply too complex to define with traditional programming. For example, recognizing faces or understanding speech involves patterns that are difficult to describe with rules. Machine learning shines here, uncovering hidden relationships in massive datasets that humans might miss. It also adapts to changing environments and new discoveries, making it ideal for fields like medicine or finance where knowledge evolves rapidly. Instead of constantly rewriting code, we let the system learn and update itself. This flexibility and power are what make machine learning a cornerstone of modern technology. Machine learning is already transforming our lives in countless ways. Think about voice assistants that understand spoken commands, self-driving cars navigating busy streets, or software that classifies new astronomical objects. Even games like backgammon have seen computers reach world-class levels through learning. These examples highlight the versatility of machine learning, showing how it can tackle tasks that range from entertainment to critical scientific research. As we continue, we'll dive deeper into how these systems are designed and what makes them successful. Build a machine learning system, we first need a well-posed learning problem. This means clearly identifying three things: the class of tasks the system should perform, how we'll measure its performance, and the source of experience it will learn from. For example, in a checkers game, the task is playing checkers, performance is measured by games won, and experience comes from practice games. In handwriting recognition, the task is classifying words, performance is accuracy, and experience is a labeled database. Defining these elements sets the stage for effective learning and meaningful results. Designing a learning system involves several key choices. First, we select the training experience, what data or feedback the system will learn from. Next, we define the target function, which is the knowledge or skill the system aims to acquire. Then, we choose how to represent this function, such as using mathematical formulas or decision trees. Finally, we pick an algorithm to approximate the target function based on the training data. Each of these steps influences how well the system learns and performs, and together they form the backbone of any machine learning project. The type of training experience can make or break a learning system. Direct feedback, like knowing the right move in a game, makes learning easier. Indirect feedback, such as only knowing if you won or lost, requires the system to infer which actions led to success or failure, a challenge known as credit assignment. Additionally, the learner might control which examples it sees or rely on a teacher to provide them. Finally, it's important that the training examples reflect the situations the system will face in the real world. Balancing these factors is crucial for effective learning. Target function is the heart of what the system is trying to learn. In our checkers example, one option is to learn a function that picks the best move for any board state. However, this can be tough with limited feedback. A more practical approach is to learn an evaluation function that scores each board state, making it easier to choose good moves. By assigning higher scores to better positions, the system can use this function to guide its decisions, even in complex situations. This step is key to translating experience into actionable knowledge. How we represent the target function affects both learning and performance. For checkers, we might use a linear combination of features like the number of pieces, kings, or threatened pieces on the board. Each feature gets a weight, and the sum gives the board's score. The learning algorithm adjusts these weights based on experience, gradually improving the system's ability to evaluate positions. This approach is simple yet powerful, allowing the system to generalize from specific examples to new situations it hasn't seen before. Learn the target function, we need an algorithm that can adjust its parameters based on training examples. One common method is the least mean squares, LMS, rule, which tweaks the weights to minimize the difference between predicted and actual values. For each example, the algorithm updates the weights in the direction that reduces error. Over time, this process helps the system make better predictions. The LMS rule is widely used because it's simple, effective, and works well for many types of problems. Complete learning system typically includes four main modules: the performance system, which solves the task using the learned function; the critic, which evaluates performance and generates training examples; the generalizer, which creates a hypothesis from the examples; and the experiment generator, which proposes new problems to maximize learning. This modular design helps organize the learning process, making it easier to build, test, and improve machine learning systems. Each module plays a unique role in turning raw experience into effective, adaptable behavior. Machine learning raises important questions. Which algorithms are best for different problems? How much data is enough to learn reliably? Can prior knowledge help, even if it's not perfect? What's the best way to choose new training experiences, and how does this affect learning complexity? These issues shape the design and success of learning systems. By understanding them, we can build smarter algorithms that adapt to real-world challenges and deliver better results across a wide range of applications. Concept learning is about discovering general rules from specific examples. For instance, we learn what makes a bird, or when to study more for an exam by observing patterns in our experiences. In machine learning, this means inferring a function that classifies examples as positive or negative. For example, predicting whether someone will enjoy a sport based on weather conditions. The goal is to find a hypothesis that matches the target concept as closely as possible, using the available training data. Learning a concept can be seen as searching through a space of possible hypotheses. Each hypothesis represents a different way to classify examples. The challenge is to find the one that fits the training data best. For example, in the enjoy sport task, there are many possible combinations of weather attributes that could define when someone enjoys a sport. By systematically exploring these possibilities, the learning algorithm narrows down the options to those that are most consistent with the observed data. FindS algorithm is a simple method for finding the most specific hypothesis that fits all positive training examples. It starts with the most restrictive hypothesis and generalizes it step by step as it encounters new positive examples. Negative examples are ignored. For instance, in the enjoy sport task, FindS gradually relaxes its constraints to cover all observed positive days. While effective in some cases, FindS doesn't answer whether the learner has found the correct concept or how to handle inconsistent data. Candidate elimination algorithm improves on FindS by maintaining a set of all hypotheses consistent with the training data, known as the version space. It uses two boundaries, the most general and most specific hypotheses. As new examples are observed, the algorithm eliminates inconsistent hypotheses, gradually narrowing the version space. This approach provides a more complete picture of what the system has learned and helps manage uncertainty when multiple hypotheses fit the data. Free learning algorithm makes assumptions, known as inductive bias, about the patterns it expects to find. If the true concept isn't in the hypothesis space, the algorithm may fail. Expanding the hypothesis space can help, but too much flexibility can make learning inefficient or unreliable. The key is to balance expressiveness with the ability to generalize from limited data. Understanding inductive bias helps us design better algorithms and interpret their results more effectively.